back. Last time, so yeah, if I make good progress today, we'll finish through 49. I think last time I had done 46. And I got a little bogged down in the details the way I was doing it. Yep. And then I didn't actually verify the coefficients that he writes here. I did it after the stream. So I might go through that right now. And then these three actually are all pretty related. They're all basically just differential equations stuff. I mean, it doesn't really involve outside knowledge of differential equations. It's just you're using this operator, and the differential equation itself involves this z dz operator again. So these ones I did look at already, although it was a few days ago, and I don't really remember what I'm doing. So I'll try those again right now. But first I wanted to talk quickly about 46 again. So like 46 review, see if I can explain it a little better. The question was, did I delete this? I took a snapshot of it at some point, but I'm sure I deleted it by now. Yeah, I did. Oh, yeah. So anyway, 46 is this one. Maybe I'll see if I can stick a picture of it up there. Just a sec. Oops. All right. May as well have left this up, huh? I didn't realize I would be going over it again. All right. So there's the problem. Question is like, well, so what I had done to start it, I mean, it's much smoother and sort of faster to do it this way. If you notice, I mean, this is a formula in n, right? So there is and it looks like a geometric series. There is evidently, so the sort of proper way to do it, there is evidently a recursive relation between fn and fn plus 1, you know. Of course, at 0, you get this over 1. Fn of 0 would be 0. So that's trivial to see, that part. So the two things I was trying to show is that at 1, you get n factorial, which is a little, you know, it's conceivable. This is a polynomial of degree n. And let's see, we're adding up like 1 plus 2 to the n plus 3 to the n. That does seem kind of confusing now, doesn't it? Well, no, this function, the polynomial on top, the numerator, if you plug 1 into that, you'll get n factorial. So this stuff equals n well, at 1, the sum of that. I'm saying one consequence of this is that if you were to sum up this stuff indefinitely, it's clearly divergent. But over here we get n factorial over 1 minus, actually you get infinity, but so never mind. This doesn't help anybody. So good. That part's consistent at least. Anyway, what we wanted to see is that this is true and also that fnz is a polynomial of degree n. And the way that he did it in the book is let's see. I don't quite remember. I don't think he moved it over. He kind of just had this relation again, right? 1 minus z to the n plus 1. And in this case, it would be 1. Well, you don't need to do that part, but... oh, I know what I'm doing. I see. Yeah, right. I mean, I guess it's good to remember this. I forgot that where this is all coming from is that it's the z d dz operator applied n plus 1 times to just the reciprocal here, 1 over 1 minus z. So apply this to a geometric series, right? If you do it once, you'll get these powers in front like 2z squared, 3z cubed, etc. But if we keep doing that, you just get more powers. So your coefficients just get larger, right? So take the previous formula. Like we know that this is... This was sort of how we defined this guy. Oh, did I do this one wrong? This is probably supposed to be n plus 2. Yeah, it is n plus 2. This would have been 2 right there. This one's n plus 1. So this is what happens when you apply it n times to this guy, right? And we get some formula. I mean, you could also just apply it to this. So if we do it again to this, you should begin to get a formula for I was going to say you should begin to get a formula for this guy. Yeah, of course you do, right? It's z dz applied to this guy. So yeah, if we do it again, you'll get a formula for, here I'll just write it down explicitly, for this. And we know that that formula is also this. Sorry, this. So that's where your relation comes from. So I've used the quotient rule on this puppy. Well, it's not quite the quotient rule, right, because of this extra z thing, but basically just do what you normally would do. Hey, Stucky. Cheers. What am I doing? No, well, I can show you the answer right away. I had done this one last time, but I'm going to go back over the way I did it. I didn't do it the way he did it. But my way also works, and I learned something in the meantime. So the question is there in the corner. There in the corner. Show that a thing is a polynomial. the numerator would be a polynomial of degree n, and that when you evaluate at 1, you'd get n factorial, right? So he does it by just, Cesaro, I think, answered this in some book in 1904. He does it by noticing this recursive relation. And then he sort of verifies the coefficients, what they would be, but it's pretty quick after that. So I was going to try to reproduce that. It's been a couple days since I looked at it. So I'm basically just reviewing number 46, even though I did it last time. But the funny thing is, I'll show you again the way that I did it. Like, the way I should have done it is what I just showed you there, where, you expect to see, if you took n plus 1 derivatives of this, you'd get this kind of formula. So we take a derivative of this guy, the n case. We take a derivative of this, which is just basically a quotient rule on that. But you know that you're going to get this back. So if I do go ahead and take this quotient rule, it's going to be, let's see, the derivative of the top times the bottom minus the top times the derivative of the bottom. Notice there's a chain rule there, so we do get an n plus 1, like that, but we also get a plus sign. And then divide by this junk squared. So 2n plus 2 downstairs. So this is what you would get if you differentiate this previous formula, the one in the question up there. So we just took one derivative, and then I forgot to multiply by z, so we gotta scale this answer by z. So what? Well, you can factor this out, of course, and it's going to cancel a little bit. So we cancel a bunch of 1 minus z's. We'll have one extra one here. So we're going to get something like fn prime z 1 minus z plus fn n plus 1. And then n of these are going to cancel. So we're going to get, I was expecting to get this, right? And we do. We get n plus 2. Cool. Halo down, dirty dogs. I guess you've been here before. For some reason, it's not telling me that you're new. Usually, it would warn me about you people. Anyway, so we're here, and you now have a formula for. So what I was supposed to do to answer 46, what you should do, the smoother way, is to just do what I just did. Like, look at the base case, take a derivative. When I say derivative, I mean this weird derivative operator z ddz that we're talking about. That's what this whole section is about. I'm on chapter 3 of differentiation of power series, but he introduces this z ddz operator and points out basically how applied to powers, powers would be like eigenfunctions for this operator. Is the intelligent way to say it. But it kind of fixes, it gives you this nice formula for powers. Because when you use the power rule, it just scales it back up to the original power when you multiply by z afterward. And so we just do a handful of things like that. Like the first couple, the first one was really easy. It was just like, if you have a polynomial of this differential operator and you apply it to a power, you just get that polynomial evaluated at the power. So that's cute. And then the next one was, if you're familiar with like Lie groups, you've definitely done stuff like this before, like show that this is a multiple of E. Anyway, so if you've played with like, I don't know what to call them, generalized operators like exponential evaluated at an operator, you'd probably do computations like this before. And I'm working on 46, although I did do it last time, so I have a bit of an advantage today. But I'll show you what I was thinking. I'm basically redoing the last talk today, and if I have time, I'll tackle these three. Because they're actually not bad. They're pretty straightforward. You're just verifying that this satisfies the differential equation. And he has a comment about solving with quadratures that I didn't understand. I vaguely know what quadrature is. But I'm going to skip that for today, that comment. So yeah, that's what we're talking about. That's what I'm focused on. Hoping to wrap this up this week so I can move on to functional equations with power series. Yeah, I haven't gotten this far before in the book. I don't know anything about these. I skipped ahead this like a year ago and did some of these because they looked reasonable. But I don't think I did these number 50. Anyway, enough of my rambling. So let me finish 46. I can show you how to do it two different ways. The proper smooth way is what we're doing here, where you just differentiate, what you've been given. I said differentiate again, but I mean use this operator. So take the operator applied to this, and you should get this, right? And so therefore, formula for fn plus 1 is this. The derivative of fn times z, 1 minus z, plus just fn times n plus 1. And that's it. That's the numerator. And so I guess our quest was to show that this is a polynomial of degree n. And also, when you plug in 1, we're trying to see that you get n factorial. But we also know, let's see. We could do f0 of 1, probably. Yeah, f0 of 1 is this numerator. Like if you don't differentiate at all, this geometric series guy, I'm just noticing that we've already got a base case. So hey, here's your induction that you were hoping for. So suppose I knew that fn of 1 was n factorial. Fn plus 1 at 1 is going to be I've made a mistake. What am I doing with my life? Well, oh well. Times 0. Oh, good. This term is gone. Ha ha ha. Lucky me. Used to be freaking out there for a second. Times n plus 1. So yeah, we're just getting n plus 1 factorial. Boom. Easy. Check that off. But yeah, we're still supposed to show that this is a polynomial of degree n plus 1. But again, I mean, if you knew that fn was of degree n, then this is now n plus 1. Like, this is degree n plus 1, and this is degree n. So yeah, check on that too. See how easy that was? Very easy. That was a quick one. So I had not done it this way. But I wanted to revisit the way I did it because I actually didn't do anything wrong. And if I had known a little bit more, I would have gotten it fine. So what I did was, well, this is a mess. Let me start over. This is Dave's approach, which, I warn you not to do, I guess. But I had looked at the series. So we get z plus 2 to the n z squared plus 3 to the n z cubed, etc. Right? This is supposedly, this is, well, you can express it as this, where fn is a polynomial, and that's what we're trying to show. So I had said, all right, I'm going to find this function. I know it's some series, right? Obviously, this is a series, and so is that. So what I did, you see where I'm going with this? I multiplied by the denominator, and I said, well, I know what that is. That's just the binomial theorem. Let's do this. And then I got negative, like that. That's just the binomial theorem, and it goes from maybe 0 to, well, it doesn't have to go to infinity. It just goes to n plus 1 in this case. So I said, well, what if I take this and I multiply by our fancy infinite series here? I should really make this j, but that's okay. K to the n, z to the n, right? I will get something. What do I get? Let's call that thing fn and see what it is. So this was Dave's approach. So of course you get, let's call them, I don't know, cj, z to the j. You get something, right? And this is an infinite series. It goes from 0 to infinity. Yay. But we have a nice formula for these. It's easy, right? You're getting these sort of cross-term things. But in general, if you want, say, the kth entry, it's let me call these AI and call this, I should have called it BJ or something, but this is BK, right? If you want CK, it's a formula like this. You know, A, K, B0, right? And I guess you're noticing B0 just is 0, so that part cancels. But the point is, it's easy to understand this at least. These are still sort of like baby series. They're not very challenging. So I get a formula like what? Well, okay. I jotted down, I guess we'll go, so for CK alone, you get like, let's say j goes from 0 to k, and then you get, let's do it slowly. You get AI b k minus I, right? So you get this binomial madness. Sure, it's alternating. And then here you get k minus I. And if I were a smarter man, wait a minute. Did I say that right? Yeah, k minus I, but it's to the power n, like that. Okay, so this sum is our coefficient right here. And so at this point, I was like, okay, that's fine, but like, why is ck equal to 0 when k is greater than n? And then I got stumped, right? I was like, it was clear to me that this had to be true, so like, what, did I just discover some new identity or something? But if you do a little Googling, because I heard the phrase like Eulerian series, but I don't know how accurate that really is. But I just didn't know enough about this series. And it turns out that this is like the, this is a formula for like the kth difference operator. So of course, if you take n of them, you'll get 0, or I should say n plus one of them. It's like the kth difference of z to the n, something like that. So that is what I discovered, and that would have quickly been like, okay, well, that's clearly 0 if you take n plus 1 differences of this function. So I figured we should probably discuss that real quick. See if I can reproduce this formula if you take k finite differences of z plus n. So what I mean by that, of course, is if you call a difference, well, let's just do it in general. If you take the difference of f to be defined as this, you know, you do it twice, you'll start to see these binomial coefficients popping out. I suppose we could prove that, you know. So if you do this again, you'll get this function plus 1, right? So you'll get like x plus n minus, oops, sorry, not n, excuse me, 2. You could do this minus the case at x, right? Something like that. So you get 2 in the middle. Obviously, you're seeing that you're getting binomial coefficients. And if you're savvy or if you've seen this before, you know this is binomial coefficients in the center. You could also prove it though. But yeah, the rest of this conversation is basically going to be me saying, well, there's a nice formula for the nth difference of a function. And if you apply it to z to the n, you'll get something like this. And of course, if you take n differences of z to the n, you'll get n factorial. Well, the leading term will have an n factorial in it. Yeah, and if you do it one more time, you'll just get 0. So that is why apparently ck does equal 0 when this k value, because I think that k is going to correspond to how many differences you've taken. So if I had shown that, that would be the end of the proof. Okay? That was my other way to do this problem. 46 was basically multiply by the denominator by your, multiply your denominator by your series that they gave you, and that's your fn function. This is fn. And our task was to show that this is an nth degree polynomial. So I'd be trying to show that the coefficients do vanish, when the index is greater than n. But I got here and I really didn't know what to do. I don't know. Maybe I've seen this once, but I was not familiar with this expression. And it turns out that it's just the kth difference equation of z to the n. Okay, and if you knew that, then you would know that it equals 0 after n steps. But let me make a teeny bit more rigorous, and then we'll move on to the differential ones, or the differential equation ones. So I'm still looking at 46. Actually, I'm looking at difference equations. See what a distraction this has been? It's a good book. I love this book. I'm like way off on a tangent, but then I learned something. And it seems like it comes up in number theory. If only I had known. So yeah, we've got this base case where you just get 1 minus 1. So this is, of course, one difference. Well, okay, let's just write down a couple. We just saw this one. So I'm seeing that they're alternating, and you do get like, so suppose you had n differences. We're going to have alternating bit. This is the coefficient. And then you also have a function that's like x plus k, like that. So I believe that's our formula. And we could really just move on if you believe me. But we can also just prove this in like 10 seconds. Okay, so that's our formula for the nth difference. Oh, you can't see that. There you go. That's our formula for the nth difference equation. Yeah, sure it is. So he says, right? Anyway, if you believed me for n minus 1, and we apply the formula to the n minus first function, we would then get, well, should we just jump to it? I mean, you should get this minus this, right? You should get a series that stops at n minus 1, alternates, and this is just the same. And then, oh, no, it's not. It's plus 1, isn't it? See that? Oops. And then you get the same thing, but with a minus. Hey, Sanictos. Thanks for popping in. I can do some calc. What is going on here? Losing my train of thought. Yeah, you're not wrong. You're not wrong. It's that. So, why am I trailing off here? This should be easy. Oh, you're trailing off because this is the wrong way to think about it. I've been doing a lot of Fourier analysis lately, so I see these like translates, and I'm like, oh yeah, get those translates together and bound them, and then take the norm. Yeah, don't do that. Don't do that. Sorry. You want these separate, baby, because so I had some junk in front of f of x plus k plus 1, and then over here I have it in front of x plus k as k goes from 0 to n minus 1. We're going to have to re-index this because we're going to see, we're going to have this kind of thing happening. Oops, we're going to have this identity, which I didn't realize, is that called Pascal's identity or something? I didn't realize it had a name. Yeah, that's Pascal's identity. So I can make this look like this. I don't know why I'm even verifying this. What I should be showing you is that when you apply this to x to the n, you're getting, sorry, yeah, like if you had a function as x to the n, your series here becomes, let's see, I guess, well, it was a kth difference, right? Yeah, but it was at n plus 1. Confusing. So I thought it was this, but let me actually just verify what it is. Because I'm getting something funky. Like, yeah, we got the alternating bit in both terms. And this is n minus 1 choose k in both terms. But I wanted to re-index this. So this is going to become k minus 1 if you subtract from the k's. Huh. It changes the sign of this too, right? Grrr. This is what I get for being so sloppy. All right. Welp. So this guy gets an extra term. I mean, he actually hits f of x plus n, whereas this one doesn't. So I'm just trying to do some trivial junk like r is k minus or k plus 1 and make these look the same. All right, so if r is k plus 1, this first is going from 1 to n. There's that extra term I was talking about. You can change this, I guess, to be r minus 1, right? And then this is x plus r, but you've got an extra negative sign. Let me just leave it alone for now. And then we're subtracting. We're going from 0 to n minus 1. I mean, I guess you can call these r if you want, right? F of x plus r times negative 1 to the r. Well, either way, all right, let's factor it out here, okay? So let's make this r minus 1, and we're adding them. And so now they look identical, except for this guy, which becomes blah from what's apparently called Pascal's identity. Yeah, so why am I still staring at this? Because there is this extra term. So this guy doesn't contribute anything for the n term. I always get confused on this step. Like I always have to pull a term off, is what I'm saying. Like I usually, I mean, it's really not necessary. Just combine them, man. But I'm always like, wait, what do I do with that extra term? So we're getting, at 0, of course, you get 1, you get fx. And here it looks like you get negative 1? Really? Sure, okay. So I'm getting negative fx. And then at n, of course, yeah, no, you're good. At n, you get fxn. I guess I'd better write it like this. This is f of yada yada. Then we get our series starting from 1 to n minus 1 of, and now you can go ahead and combine them if you want. It's n choose r, x plus r, with this alternating business. So at n minus 1, that agrees. You know, if we just plugged in n, it agrees here, it agrees here. So that last term I could have just left. And at 0, also, it agrees. So I don't know what I was nervous about. We're getting 0 to n choose r, x plus r, with this alternating jazz. You can do that plus 1 if you want. So I was off a little bit, right? I'm just off by a negative sign. It should be apparently it's the negative of this. That was the only mistake with my guess. Probably should have been able to see that it was the negative of this. Oh, yeah. Of course it's the negative of this. Good. All right, so it's the negative of that. Cool. All right, anyway, way too much proof going on here. That was proof that this is true. And then if you apply that to this function, we should be able to see that, I mean, you can reason that it would give you 0 if you actually take some differences. But also it's going to give me the formula that I had. Okay. And that was all I was trying to see, is that the formula becomes 0 when k is larger than n. So our series was ck being, I got, well, sure, we can just copy this, but the point is going to be that when you plug in k larger than n, this becomes 0. You can use k again if you want, I guess. It's alternating, and you got the k minus I business. K minus I to the n. It goes from 0 to k. That's what I had, and I was trying to show that this equals 0 for large k. For this function in particular, we're going to get just this, right? Yeah. Nothing ever happens to that f, so you just leave it. So it's to the n, excuse me. Confusion. I had done this the other day after the stream. I like kind of verified that it would happen. But anyway, now all I'm doing is trying to show that these are the same series. Um, yeah, what are you doing here? If I had like x, it would definitely take two differences before it, right? If you take a second difference, you'll get 0. So when you do this to like a linear, anyway, this really has to be greater than k. If you actually do it k times, I'm expecting to get, k factorial. I don't know why I'm stalling here. Where did I have it in my notes? Do they help me? No, my notes are even worse than what I'm scribbling here for you guys. Did I do a second sum? Did I take binomial theorem? Looks like I did. Yikes. No, I think I ended up at the same position. Yeah. Kind of ended up at the same spot. Why do these look subtly different, you know? I'm gonna pause here for a sec and stare at things and poke around and check my phone. All right. I'm back. Yeah, I had notes from the other day, but they just say the same thing that I just showed you. I basically just got here. And I was like, oh, great, that's the same. So first of all, well, no. What did you want to say? I mean, there's a couple of things that are being conflated here. I wanted to apply it to this in particular. This is the nth difference. So I guess this is not going to give me 0. This is supposed to give me n factorial when I'm done. But if I did it again, if I just change these numbers to n plus 1, not this number, but these two, if I change them to n plus 1, I'm expecting to get 0. Okay? And the other thing is why, like, I still have an x, which is confusing me for some reason. But the important bit is that I have an r there. Why? So yeah, I'm clearly like right there. I just haven't clearly stated what I'm doing. I mean, what else? If this was bigger than n, say n plus 1, you'd still stop at n plus 1 here because of this term. And also, this is actually the nth difference, which is not the one I wanted. I want to go n plus 1 to show you that from then on it'll be 0. So that'll change these two numbers. That'll be good for me. These will match up. Is this correct now? Yeah, there's like an extra negative sign, but so what? Yeah, I is changing. Here, r is changing. Why does it look... Oh my god. X plus k. Grrr. Yeah, why does it like... It looks so close, but not... I don't know. Clearly I'm going to have to think about it again, I guess. We were going to let k be, you know, n plus 1, for instance. Because anything higher, this still just caps off at n plus 1. And we get 0 to n plus 1, and then the rest of it looks the same. There's not really much to say there. It's alternating. This k becomes n plus 1. And it's still being raised to n. This n came from, I forget our formula, but I guess, yeah, it came from the BKs, like this coefficient. So that's why it's a fixed n. It's coming from the original question, you know? And then this, I really should change these to n plus 1 because I'm taking n plus 1 differences. But yeah, I was trying to say that these are the same. This one doesn't change. Oops, this one does. Damn it. This one does. That's an n plus 1. So I was trying to say that these are the same series, but I'm getting confused on this term now. I guess I'm just being stupid. But we could move on if since this is not super interesting. I was just trying to show that our series is identical to the nth difference of a power. And since you know that that's going to vanish after n plus 1 differences, so does our series. I mean, you could evaluate at n plus 1. That doesn't actually change anything. So now all I have to deal with is the stupid minus sign. Wait a minute. Aren't I off by 1 minus sign? I'm a little confused still. But, like, you could take this function and evaluate at x equal whatever you want, it's still going to give you 0 after n plus 1 differences, you know what I'm saying? So let's do it at n plus 1, evaluate it at n plus 1. But then I still have a minus here instead of a plus. But we do have an extra negative. Is that helping me? It doesn't seem to. We could factor, no, I don't get it. I'm not seeing it. This order doesn't matter. And if you then negate, like if I factor -1 to the n out, maybe I'm wrong about this. Maybe that's actually supposed to be the negative of this value. You sort of see what I'm driving at? That right-hand side, I could... It still doesn't match up here. You only have one negative. You don't have n of them. Yeah, stupid little details. Like if I negate this, sure it matches, but then I only have one negative. I don't have like n of them. But I'm very close, right? Yeah, so for some silly reason, these are the same. Like, I could evaluate x being negative n plus 1 maybe, and then factor out -1 to the n, and like voila, something happens. I mean, by something happens, I mean I get a negative r, is what I'm trying to get. Well, anyway. So this right-hand side, you've got this, then you've got this, then you've got this, right? And on the left, I have -1. Let's change them to r this time. And I have n plus 1 minus r. And I'm trying to figure out why those are identical. Obviously, you could let x be the negative of n plus 1. It doesn't change anything, except that it makes this match up. So now I'm just asking why. -1 to the n minus 1 is 1. You see what I'm saying? If I divide by -1 to the r, it's identical as long as this is true, but it should just be identical all the time. I should probably move on since I'm good up to a single negative sign now. Right, like it's clear for odd n, but that's not the point. It's true for every n. So yeah, I'm not gonna fish out where I made a mistake there, but this was a little scribbly. Sorry for that. That was the nth difference. So the reason I brought that up at all is that this is the way I had done the problem last time. Was I just multiplied by this denominator, and I was like, okay, I get something. Prove that that thing is finite degree. And so the next step would then like show that this equals 0 when k is larger than n. And I was like, I don't know why that would be true. That doesn't seem to be true. But it turns out it is exactly true, because this is a difference equation. Like this is the kth difference of z to the n. So if you plug in n plus 1 up there, you'll go off on some adventure and you'll theoretically get what I just got. All right, we should get back to the story. It's been way too long. That was 46. Believe it or not, that was a review of what I did last time. Well, not really. I didn't talk about it in detail last time. I didn't know what I was doing last time. If you can believe that I know what I'm doing now. All right, so I'm looking at 47 now. I'm going to kill this. I should probably just put it on screen, but I'm feeling a little too lazy to do that. So here's 47. You have two polynomials. G doesn't vanish on integers so that you can divide by it. Okay? And then you want to show that this series solves this differential equation. And again, when I say differential, I mean z d dz. So you differentiate and then you multiply by z. So I'm probably going to screw this up, but believe it or not, it just pops out. Like if you just plug it in, it'll work. So take f0, g0, f1, g1 as coefficients, etc. Right? Yada yada. I'm supposed to show that this apparently solves. What are we doing? 47. Apparently this solves this sort of polynomial differential operator, like g applied to your operator, apply that to y, and supposedly it'll be the same as applying f to, where are we? Oh, yikes, to this guy. You know what? I'm remembering now. His answer is just like the left-hand side equals. It was just like the left-hand side equals the right-hand side. That's his answer. I could be lying, but I'm pretty sure all he says is write out some terms. The left-hand side equals the right-hand side. We are done. Okay, fair enough. So why would that be? Well, when you apply it to, so we know that from a previous, all of this is hinging on 44. That I proved like last week at some point. If you have your polynomial differential operator and you apply it to a power, it just evaluates the polynomial at that power, at that exponent. So if you knew that, this problem becomes a lot easier. So that's our left-hand side, basically, because this series y is just like a, well, it's not a geometric series, but you can see how it's a bunch of powers. So recall that when you take this operator and you apply it to a power, it just evaluates at the power, and you get the original. It basically just scales that function. So in fancy language, this is an eigenfunction for this operator. Yeah, man. So what's going on over here? That means, well, for the first one, I guess you get 0, right? But for the next one, you get, the left-hand side is then this number times g of 1. Awesome. And then the next one is f2 over g2 times our polynomial. There's a z squared here, you know? So you get g of 2. Oh, did I forget the... Sorry, I forgot the variable. Etc. You keep going. So here you're getting like this operator applied to z cubed. You're going to get the polynomial at 3 times the original. Oops, there's a 3 there. All right, so it moves on like that. These cancel, obviously, and I'm getting f1z, f2z square, etc. Is this obviously, well, oh yeah, it is the same as the right-hand side, because the right-hand side is just, it's like, okay, we can do the right-hand side separately if you want, but it really is obviously happening. Take f of z d dz applied to this geometric series, right? And you're getting 0 plus f1z plus f2, right? So boom, Bob's your uncle. I guess. I don't even know where I got that expression. But they're equal. Yeah, they're equal, man. Yay. For once, an easy problem. All right, let's look at 48. Suppose f and g are relatively prime. G is not smaller than f. That's fine. G of 0 is 0 for some reason. Anyway, suppose the g's don't vanish on integers and you get the series. And we want to show that this new series, these wacky product coefficients, satisfies this madness. So this time your right-hand side is a z times y. And we've almost got a more interesting differential equation because both sides involve the function, you know. But anyway, I don't see myself simplifying this one. I mean, other than the zy, I guess we could scale this. I'm betting it depends. Yeah, it was too easy. You gotta take the W's, right? It was awesome. Oh, it's a good one. We can talk about it again. All you do is check the left-hand side and the right-hand side. It definitely hinges on this. It's just this fact. So this operator, when you apply it to the ZD-DZ operator, the cool thing is that when you apply it to a power, you of course get the power rule, but then it scales it back up. So what's just kind of cute about this operator, you know, like for the regular derivative, these are eigenfunctions, I guess, right? But for this operator, a power is an eigenfunction. So it's handy. I don't know how handy. But I mean, I guess it's allowing us to do stuff like to answer this kind of question, to realize like this is this fraction where the top is a polynomial of degree n. As for these, I don't know. These are a little contrived, right? It's like if you had this, it's going to allow us to solve like 47, 48, and 49. Nope, you can't see it. There it is. So this operator like allows us to do this, but also, you know, they sort of came from the operator. So maybe, you know, maybe not such a big deal. But, you know, different differential operator than the regular DDZ. That's cool. It's cool to be slightly familiar with it. And then this one, but this has been, you see this kind of result when you need it, I guess. I saw this in like Lee groups many years ago. I think it was a pretty similar statement. Anyway, I'm babbling. What are we doing now? I guess you're saying, I think we don't have a first term. What was it again? I could probably like screenshot this. Maybe I will. Where are we here? 48. Oh, so one thing I did skip on this last one, it says this is soluble by quadratures. And I don't know what the hell he's talking about. Let's look at his answer, actually. It's not going to explain the quadratures part, but this was the one I had just done. Oh, I also forgot I was going to verify this coefficient thing. That's all right. We'll skip it. It wasn't that tough. Did I skip the case of it being a constant? Did I make this like way too easy? Am I looking? No, that's right. That's right. Huh. Yeah, he did it. He like phrased it a little differently than I did. But like he first showed that it holds for constants, for constant g, and then he basically used an induction argument. I remember being stuck on this part for a while. getting from here to here. But and then he makes this comment about being solvable by sorry, you can't see it. Then he makes this comment about it being solvable by quadratures, but I don't really know what he's talking about. I'm vaguely aware of the quadrature method for integrals. So this could just be, I mean, I don't think I ever saw it in school, to be honest. It could be like a numerical, it could be something that's like in numerical analysis more often, and I'm just not familiar with it. Anyway, that doesn't help us. The one I'm working on now says both sides are equal to this. So it looks like I got it wrong. 47 I thought was 48. That's why I just jumped into 47 and did it as quickly as possible. But yeah, what's 48 again? I was going to take a screenshot, but then I got lazy. Let's just dot it down. 48, there it is. So we got 1 plus f1 g1 z plus f1 f2 g1 g2 z squared, etc. Anyway, this one works out just like the last one. Making me nervous about the last one now. Anyway, this one's supposed to solve the same thing but against zy. That's the question. And then if we do that one, you're seeing that 49 is just is like one application of that. The numerator, like I could come up with f and g, where g of 1 is 2, okay? Like g of 2 is 4, g of 3 is 6, you get the idea. And then upstairs, we're getting odd powers, so like f of 2 is supposed to be 3, f of 3 is supposed to be 5. So obviously we can dream up a pair of functions that do that. They're relatively prime, even. Oh, they're squares. I'm supposed to square those numbers, but yeah, you get the idea. It's going to be the same. So 49 is just 48 applied, clearly. But yeah, there's 48. So yeah, boom, problem. I'm looking at 48. But yeah, 48 is going to be very quick. I'm wondering why he made a bigger deal about 47 now. He basically showed that like in the question, there are two arbitrary polynomials. G doesn't vanish. Get this series, satisfies this. I basically did it. I don't really see what would have been wrong with what I did. I just took the f operator applied to, here it is. I took the g operator applied to our function. And then I took the f operator applied to this geometric series. And so f operator applied to that gives you, I mean, it just gives you this, which is the same thing. All the g's cancel. Yeah, I'm not sure what else there is to say about that. He had done it, he first says, okay, what if g is a constant? And he concludes that it's true. Using the 44 means this fact, you know. So he's like, well, it's true if g is a constant. So does what I did fail if g is a real polynomial? I don't understand. Did I screw something up? No, it's fine. I don't see what I did wrong. I don't think I did anything wrong. And then he says this applied to blah. This this is basically one more application of, he's doing it sort of by induction in a sense. Well, he's just saying if you had a smaller order polynomial g1 that we assumed it was true for, then you could write it like this, and that's it. It basically just falls out. So I was staring at this for a while to get from here to there, but now that I just did it really fast, I don't really see what was wrong with what I did. I'll have to think about that again. I don't think I did anything wrong. Well, there was nothing unique about f and g. I just applied the same result. I just applied 44 to both sides, and the answer pops out. Anyway, without further ado, the same thing's about to happen with 48. If you take this junk, right, and you apply it to this stuff, again, we have a bunch of powers of z, so that's awesome. We can use this result again. Makes it pretty easy, I think. So g applied to this whole function is going to give you 0 plus, here the g1s cancel. Here it's not quite the same. Here the g2s cancel, but you still get a g1 in the denominator. So here's my left-hand side. I'm saying you're going to get 0 plus f1 g1, and then when you apply g to z, you get g of the power times the original function. And then same thing here, we have this coefficient, and there's a g2 there in the denominator, but when you apply g, the differential operator, to z squared, you get, of course, g of 2 z squared. So these are going to cancel. You're basically getting a sum where you have like a few integer values of f upstairs, and you have the same ones downstairs, except the last one gets canceled. So here, like, when we apply it to z cubed, you're going to get g3z cubed. The g's cancel. Well, just the g3's cancel. So, of course, you get f1 z, f1, f2 over g1 times z square, f1, 2, 3 over g1, 2 z cubed. Okay, so that's our left-hand side. We could write that down if you want, but I mean, I get we could write it down, but I don't really feel like it. But yeah, it's what? It's a product. It's a product of fi from 1 to n, zn over the product of gi from, one fewer. You can see what it's doing on the left-hand side. The right-hand side, I'm certain, does the same thing. Here's the right-hand side. It's f applied to, this time it's applied to zy. Well, we don't need to do a product rule. Let's just scale y by z. Okay, so you're going to get a z in the first term, and so right at the gate we get f of 1 times z. For this applied to z times y. Like, I'm saying zy is, of course, z plus 1s against z squared, etc. So the scale of z has gone up by 1 power. So on the second term, we had this, but we're applying f to z squared, so you should now see f2 z squared. And then on the third term, we have this as a coefficient for y, but we're applying f to z cubed, so we should get f3 z cubed. And hopefully you're seeing these match up. So that's it for 48. Wild stuff, huh? Yeah, I still feel like these are a bit contrived, but there are some, I don't know, 46 seemed like a neat, 46, the one I was talking about for the first hour, seemed like a neat, it's just an interesting application of that operator. That's probably the most interesting problem I see here. These ones really feel like you cook them up just to have something to do with this operator. Like, when would you ever... Well, on the other hand, these functions are kind of nice. The function itself is cool. So if you were like, I have this function, what differential equation does it solve? That could be useful. I could see that being maybe helpful. Because like these seem like pretty natural functions to show up. Especially here's an application. So 49 is, if you had this function, show that it satisfies this. Oh, did I cut it off? Damn it. Maybe I didn't. No, I didn't. Sorry, you can't really read it anymore, but yeah, I didn't. So I'm looking at 49 now. I thought I cut it off for a second, but I think this is going to be my last one for the day. But hopefully it's a quickie. I got to go mow the lawn. But I can chat for a minute if you had any other questions or something. This is against z squared, yada yada, you get the idea. And I want to show that this satisfies z1 minus z, oh no, second derivative. 1 minus 2z dy dz minus a quarter y. So I did do this one on my own like a few days ago. So I know it works, but I don't remember any special trick about it. But we just did 48. So like it's clearly just 48. We're going to let f be the numerator. Those are odd powers. So we're going to want it to be like 2. This is 1, right? So we want it to be, I guess 2z minus 1 squared. And g of z, we want it to be even powers. It's okay that g of 0 equals 0. But for the rest of them, g of 1 is 2, etc. squared. So yeah, just take this and use 48. That should be all we need to do. For once, I've got a couple problems that were quote unquote easy. I don't want to expand this or anything, but we do know that, yeah, we just saw the one that was like, what was it, 1 plus? Yeah, it says 1 plus. We just saw that this junk, well, sorry, I should write out an extra term. Was it F2, G1, G2, Z squared? Yeah, so this junk solves whatever on earth I had just written down. I guess it solves like G against Y equals F against ZY, right? Yeah, sometimes Polya is nice to you. Not often, but sometimes it's a very obvious setup. He just like cues it up. He's like, you couldn't possibly miss this, right? After you spent 2 hours reading his previous answers. Actually, let's just see what he has to say. He probably doesn't say anything. Yeah, 49, apply 48. Oh no, I screwed it up already. Oh no, I didn't. It's fine. I did 2x minus 1. I see. So he's going to be off by a factor, some constant. So, oops, sorry, you can't see it. So yeah, here's 49, just says use 48. Hey, Serene. So his answer was clearly just do exactly this. His only change was, for some reason he looked at like a quarter of this, which doesn't matter. It's just a multiple. So of course it's still going to satisfy the equation. But For some reason he did z minus half squared for that top function, which doesn't make a lot of sense to me because, well, it does because you can scale it, so it's a moot point. Never mind. All right, we're almost done here. This is too easy, right? Here's our function. It agrees with this function, obviously, and we already know that this solves this one. So I just need to show us that, like, if you did 2z ddz squared times your function, you'll get this stuff. So I would have done it this way. Oops, you screwed it up already. Damn it, damn it, damn it, damn it, damn it. It's 2 operator minus 1 squared applied to zy, okay? So I'm trying to show that, well, I don't actually have to show anything. I just need to verify that, like, that this, what I just wrote down, agrees with that differential equation that he wrote down. So now I'm just checking that the differential equation you get from this is the same as the differential equation you get from this, or at least a multiple of it. It's probably going to be accurate up to the multiple 4, because he had divided by 4 in his f function. The second, well, okay, yeah, you sort of get 2 derivatives there, but do you really? Actually, there's no point in talking about left-hand side versus right-hand side, because we're just going to boop them all on the left and see that it's equal to this. Yeah, right. I have a lot of chess books in the basement too that I never sat down and went through. Well, I read them, but you know how it is, like with the real books, like, what am I going to play through every single game? Because I can only see maybe 10 moves in my head before it starts to fall apart. I need a board in front of me to do those, and then, like, what I'm going to analyze the game, and yeah, you got to actually sit down and do it, or else it doesn't happen. I mean, we can do twice, but, like, it doesn't just do this. I have to, oh, you know what it does? Okay, just do it, I guess. The 2, though, the 2 doesn't change anything. We could probably just do 4. This happens twice, okay? So this you should be a little careful with, because when you do it once, you get zy. When you do it again, you're going to get a product rule. That's how this is going to, that's how this is going to pop out. Like, you're getting this big expansion of stuff. And then over here, he had factored a 4 out, which I guess we should do. It doesn't really matter. What was wrong with my function? Nothing, right? If I plug in 1, you get 1. 2, you get 3. Okay, I'm going to stick with this and see what happens. Anyway, what I'm babbling, the only interesting thing about this verification really is that you're about to see a product rule, right? We get y prime, of course, which we have some y primes involved in the question. But yeah, you're going to actually get, like, zy prime, right? And then we apply this operator to it again. So you're going to get a product rule. Z ddz of z is, let's see, you get the derivative of the first times the second plus the first is now z squared times the derivative of the second. So that's our product rule with this operator applied to this. And there's a 4 in front. That's our left-hand side. The right-hand side, eesh. Starting to regret that 2 being there. It doesn't matter. That doesn't matter at all. This operator applied to this operator applied to zy, okay? When you do it once, you get stuff minus zy, so let's see what you get. Yeah, what do you get over here? Well, it's the same. Didn't we just do this? Sort of. Yeah, we basically just did this. But let's do it slowly, I guess. 2 of what? 2z times. So if I differentiate this, I should get y plus zy prime, right? So here's y, and here's zy prime. And then, oops, no, that's okay. That's okay. That's correct. And then just do it again. Eesh. I mean, I could do -1 easily enough. Do any of these combine? Oh, look, it's z. Cool. All right, maybe I should slow down then. This is just zy plus 2z squared y prime, right? Okay, so for the first one, well, all right, we're also getting this for the easy part. But for the first one, 2z ddz of this stuff, you get 2z times the derivative. So you're getting 2z times y. That's first derivative of the first times the second plus the first times the derivative of the second. And then I almost missed this guy. We're also doing that one. 2z times the derivative of this stuff. So 2z times 4z. That's the derivative of the first times the second. That's 4z times that. Derivative of the first times the second plus the first 2z squared. Looks a lot like this times the derivative of the second. And then you get these two terms as well. All right, so this equals this. In other words, 0 equals, I'm glad we have no triple derivatives. That would be bad. 4z cubed minus 4z squared. That's in front of the second derivative. And then there's a single derivative here, so -4z. Let's see. I got 2z squared minus 2z squared. Sweet. So that's gone, but this is still there. 8z squared minus 4z. And then there's a constant. Well, I said constant, but I mean the single y. 2z minus z. And this stuff equals 0. And that's it. And so apparently this is the same as this junk upstairs. We've got a z everywhere. We could factor that out. So I see this is the same as, we could also, no, we can't divide by 4. Yeah, we can. We should divide by 4. All right, so divide by 4z, excuse me. And you'll get z squared minus z double prime plus 2z minus 1, yep, plus 1/4 y, which looks awfully familiar. Oh, yep, it's the negative of this, isn't it? Yep, z squared minus z. Okay, so take the negative of this, and we're good to go. So if you multiply by -1, you're seeing exactly this, which was the question. So yeah, that's a cute one. It's rare that I get to draw a smiley face on my work. It's mostly frowny faces and confusion faces, but not today. Thank you, Polya. Thank you, lads and lasses, for hanging out and watching my struggle.